In this video, we're going to develop a couple of different notational systems for talking about permutations. So in a previous video, we talked about the symmetric group S sub n, which is the set of all bijections from 1 through n of that set to itself. So the set of all bijections, or rather the group of all bijections, of the set of integers from 1 to n to itself, and the group operation is composition. Now in this video, and probably in most of what we'll do from now on, rather than calling these bijections, we're going to call them permutations. A permutation is like it's a special name for a bijection of a set to itself. And that name kind of makes sense because you may have learned in your previous mathematical experiences that a permutation is a reordering of something. So for example, I could take the numbers 1, 2, and 3, and map those respectively to say 3, 1, and 2. And that would be a reordering of the numbers from 1 to 3. Another one would be taking 1, 2, and 3 and just mapping them respectively to, well, 1, 2, and 3. That's not a very interesting reordering, but it is a reordering. It's called the trivial reordering, or maybe the identity reordering. So anyway, in this video, we're going to talk about the group S sub n. We're going to talk about how many elements it has, and we will develop a couple of useful notational systems for talking about permutations in S sub n. So here we go. First, let's talk about something called array notation. The idea of array notation is pretty straightforward. In some previous videos, I think I talked about the idea of taking a set and representing a mapping using an arrow diagram. So like maybe 1 and 2 get mapped to each other and 3 and 4 get mapped to each other. That's one way of representing a permutation. But another way, which doesn't require quite as much drawing, is to write down square brackets as though you're going to set up a matrix. And then write down in the top row 1, 2, 3, and 4. And in the second row, which will be the bottom row, write down the image of each of those numbers. So 2, 1, 4, 3. Here's another example. Suppose I have 1, 2, 3, and 4, and this time I send those respectively. Sorry about the poor drawing. I send those to 3. Let's go to 1 on this one, and then 4, and then 2. So this one in array notation that I'll be represented by, again, I'll put 1, 2, 3, and 4 on top, and then 1 goes to 3, 2 goes to 1, 3 goes to 4. That's funny, 3, 1, 4, I didn't plan that. And then 4 goes to 2. Well, that's it. Although I guess if you round pi to just 3 decimal places, it really is 3.142. So that's kind of fun. Anyway, that's array notation for a permutation. And of course, you can do this for the set of 4 numbers, 1, 2, 3, and 4. You can also do it for a larger set or a smaller set. So that's one possible notation. Now let's talk about, before we introduce another notational system, let's talk about in this system how you would compose permutations and how you would invert permutations. In other words, how do we carry out the group operation? So how do we compose permutations? In the previous video, we talked about how when talking about permutations, we're usually going to use Greek letters like alpha and beta. So let's let alpha be this permutation. And this time we'll work in S sub 5. So these are going to be permutations in S sub 5. So permutations of the set 1, 2, 3, 4, 5. So let's use that as an example. And then beta will be the permutation 1, 2, 3, 4, 5. And let's have those go to 1, 5, 4, 3, 2. Then I might want to ask myself, okay, what is alpha beta? What is beta alpha? Now the thing to remember here is because these are functions, I'm always going to perform the permutation on the right first. So alpha beta is going to do something to the numbers 1, 2, 3, 4, and 5. That part I know already. The question is, what does it do to each of those? All right, so let's just chase this down. I'm going to draw, for this one, I'm going to use blue arrows to represent what I'm doing. So let's see, what does alpha beta, beta first, then alpha, do to 1? Well, beta takes 1 to 1. So then I go check on what happens to 1 over here, and 1 goes to 3. So 1 goes to 3. What about 2? Well, beta sends 2 to 5. So now I come over and look at what's happening to 5, and 5 goes to 2. So that means that 2 goes to itself because beta sends 2 to 5, and alpha sends that 5 back to 2. What about 3? Well, 3 goes to 4, and then looking over here, 4 goes to itself. So 3 goes to 4. 4 goes to 3, and then looking over here at what 3 does. I did not count on this getting quite so messy. Sorry about that. 3 goes to 5. So 4 goes to 3, which then goes to 5. That means 4 goes to 5. At this point, we had better hope that 5 ends up going to 1. Otherwise, we've either made a mistake or maybe we wrote down something that wasn't a bijection. But let's check. 5 goes to 2, and then 2, 2 goes to 1. So that's good. 5 goes to 1. So now we have the permutation alpha beta. And again, keep in mind, beta is the one that gets performed first. So now let's try calculating beta alpha. Again, we'll figure out what 1, 2, 3, 4, and 5 each go to. So this time we're performing alpha first. I'm going to do this a little bit faster and just use my spotlight because I don't think I want to clutter up the picture anymore. So I'm performing alpha first. 1 goes to 3, and then I check what 3 goes to. 3 goes to 4. So 1 goes to 4 by way of 3. 2 goes to 1, and then 1 goes to itself, so 2 just goes to 1. 3 goes to 5. 3 goes to 5, and then I check 5 goes to 2. That means that 3 goes to 2. What does 4 do? 4 goes to itself under alpha, and then beta is going to map that 4 to 3. So 4 goes to 3. So I'll bet we're going to have a 5 here, but let's verify that. 5 goes to 2, and then 2 goes to 5. So 5 really does go to 5. Notice these are different permutations. I actually kind of thought they would be different. I figured that if I wrote down 2 basically random permutations and composed them in different orders and ended up with the same thing, it would be a minor miracle. But these are different. And therefore, one thing that we know straight away is that S5, it is a group. We proved that it's a group in the previous video, but it is non-abelian. Good to know. And in general, S sub n usually is non-abelian. S sub n is non-abelian as long as n is greater than or equal to 3. And that's something we might prove later. Okay, but let's introduce... Oh, before we introduce another notation, let's talk about inverses. How do we find an inverse of a permutation? So let's take our alpha again. Alpha up there was defined to be the mapping of 1, 2, 3, 4, and 5 to 3, 1, 5, 4, and 2 respectively. Okay, well, one way that we can find an inverse of alpha inverse just needs to be the function which undoes this mapping. So I could just flip the whole thing upside down. And that wouldn't be the worst representation of what alpha inverse has to be. That does tell me what everything needs to go to. So 3 needs to go back to 1, 1 goes back to 2, 5 goes back to 3, 4 goes to itself, and 2 goes back to 5. But I might go ahead and rearrange this so that the inputs, that is, the numbers on this row, go in the appropriate order. So I just need to make sure that my correspondence is the same. 1 still goes to 2, 2 still goes to 5, 3 to 1, 4 to 4, and 5 to 3. Okay, and these two permutations are inverses of each other, and you can actually check that out. You can try composing them. If I try composing them alpha first, then alpha inverse, so this one, then what does 1 do? 1 goes to 3, which then goes to 1, so 1 goes to itself. 2 goes to 1, which then goes back to 2, so 2 goes to itself, and so on. So that means that alpha inverse, or rather alpha inverse alpha, is the identity permutation. By the way, the identity permutation, you may have already figured this out, but that's just the one that maps everything to itself. So anyway, that's the array notation for permutations. One thing that this is useful for, the array notation, is figuring out how many permutations are there in S sub n. So there's a little sub-question here. Well, let's think about S sub 5, just as an example. If I want to create a permutation of S sub 5, then I need to take these 5 numbers and decide where each of them goes. And those choices can't be totally independent. Once I know where 1 goes, I can't have 2 go to the same thing. I can't have 3 go to the same thing. So I do know that if I'm defining some permutation alpha, 1 will have some destination, which I'll for now call alpha of 1. And how many choices are there for that? There are 5 choices. 1, 2, 3, 4, 5. But now, when I define alpha 2, I am constrained. I can't use the same number that I used here. It has to be one of the other 4. So that means there's 4 choices for what I'll do here. And then when I define alpha 3, there's only 3 numbers left. So I only have 3 choices for that. And then when defining alpha 4, I only have 2 numbers remaining. So there's 2 choices. And finally, when defining alpha 5, there's only 1 number left that I can use. So I only have 1 thing left that I can do. So 1 choice. There we go. So how many choices or how many ways to choose the permutation are there altogether? Well, I had 5 ways to start out. And then for each of those 5 ways, there's 4 ways I could continue. And then for each of those, there's 3 ways that I could continue here, define this. And then for each of those, there's 2 ways I could define this. And then by that time, I'm stuck. I only have 1 choice on how to finish. So the total number of permutations in this group will be 5 times 4 times 3 times 2 times 1, which is 120. But really, I prefer to just call it 5 factorial, the product of all positive integers up to and including 5. So in general, S sub n, by the same reasoning, will have n factorial elements. And that's because when I'm deciding what 1 goes to, I have n choices. And then when deciding what 2 goes to, I have n minus 1 choices. And so on and so on. I end up multiplying all of the integers from n all the way down to 1. So this is just another representation of that. Okay, so that's the cardinality, or the order, of S sub n. Now let's talk about one more notational system. So for this, I'm going to back out a little bit so I have some room to work, but I'm going to use some of the same permutations I wrote down earlier. So let's again take alpha to be this permutation. 1, 2, 3, 4, 5 gets sent respectively to 3, 1, 5, 4, 2. So what I'm going to do is I'm going to try and write down a more compact notation that tells me what this permutation does, that doesn't require me writing down 10 different numbers, the 5 inputs and the 5 outputs. So this is called cycle notation. And it'll become apparent why I call it cycle notation in just a moment. So I'm going to start by writing down the number 1. And then I'm going to write down what 1 gets mapped to. In this alpha here, 1 gets mapped to 3. And then I'll look at what 3 gets mapped to. According to this, 3 gets mapped to 5. So the next number I write down is 5. And then what does 5 get mapped to? 5 gets mapped to 2. And then 2 gets mapped back to 1. Rather than writing another 1, I'm just going to close the cycle there, because my notation is going to be set up so that the reader will infer that this goes to this, goes to this, goes to this, and then when I run out, when I reach a parenthesis, a right parenthesis, I assume that means that 2 goes back to 1, and indeed it does in this case. Alright, so now I set up a separate cycle for anything I haven't picked up yet. It looks like I've picked up 1, 2, and 3, and I've said what those all go to, but I haven't talked about 4. Well, 4 just goes to itself. So that's actually the end of my cycle. When I reach the end of the cycle, whatever number is next to this goes back to the number at the beginning of the cycle. And in this case, both of those numbers are 4. So that's the cycle notation for alpha. And I'll actually write down that alpha equals that thing. All right, so let's try writing down another one. What if I say beta equals 1, 3, I don't know, 4, and then 2, 5. By convention, we usually start the cycle with the smallest number in that cycle, but it's not required. We can start with any number we want. And of course, we can't always have things in increasing order. Like if I write the cycle 1, 3, 4, that's very different from the cycle 1, 4, 3. And both of those are perfectly valid cycles. So the fact that these numbers within each cycle are in increasing order is total coincidence. It's just a feature of the example I made up. So anyway, let's say beta is that permutation. How would I write that in array notation? Well, I just write down what everything seems to be going to here. And in this case, 1 goes to 3, 3 goes to 4, 4 goes back to 1, and then 2 goes to 5, and then 5 goes back to 2. So that's the array notation for beta. One more thing I'd like to do before wrapping up. We're actually going to do a lot with cycle notation in this course. That's really the standard way of working with permutations. Anytime you see group theory that involves permutation groups. cycle notation is the most compact way of doing business. So one thing I'd like to do is try writing down a couple of different permutations. Let's try permutations in, let's try S5 again. I don't want to make things much bigger than that. So let's try alpha equals, I don't know, 1, 2, 5, and then 3, and then 4. So alpha is going to leave two things fixed. It sends 3 to itself, it sends 4 to itself. And let's let beta equal 1, 4, 2, 5, 3. One thing I would mention is that if 3 goes to itself and 4 goes to itself, sometimes we just leave those cycles that contain just one element off. We'll just say alpha equals 1, 2, 5, and then leave it at that. And we'll omit these. If I omit these, it means that 3 is fixed and 4 is fixed, because you don't see them going anywhere in this notation. So what happens if I compose alpha and beta in one order and then in the other order? Can we work these out just using the cycle notation without having to write down the arrays for alpha and beta? And I think that we could. I think that we could absolutely do that. So let's see, we have alpha, beta. That's alpha is 1, 2, 5. Beta is 1, 4, 2, 5, 3. And remember, because beta goes on the right, and we always do the function on the right first, we're going to perform this permutation before we perform this one. Beta alpha, going to be the other way around. Beta is 1, 4, 2, 5, 3. 3. And then alpha is 1, 2, 5. Okay, let's see if we can compose these. So I'm going to try and construct what alpha beta is in cycle notation, just by sort of dynamically moving through this representation here. So let's start with 1, see where 1 goes. All right, my permutation on the right has 1 going to 4, and then over here, 4 doesn't do anything. 4 stays put. So 1 just goes to 4 and doesn't do anything else. 1 goes to 4. Now, what does 4 do? That's the next step in my cycle. Well, here 4 goes to 2, and then 2 is what gets passed over here. 2 goes to 5. Now I want to clarify something, because you might wonder, well, why don't we actually look at the next thing that 2 goes to here? And I want to be really careful about that. So 4 seems to be going to 5, but why is that? I think of these as two functions. This function maps 4 to 2. That 2 gets passed to the next function, which maps 2 to 5. So I have 4 going to 5 overall. Now what does 5 do? 5 here goes to 3. So 3 gets passed to this function, which does nothing to 3. It just leaves 3 stays put. So 5 goes to 3 altogether. And then what does 3 do? 3 goes to 1, and then 1 goes to 2. So again, 3 goes to 1 under this function. That function passes 1 over here. 1 goes to 2. So overall 3 goes to 2. And then I think that's going to be it. But let's see what happens to 2. 2 goes to 5 under this function. 5 gets passed over here. 5 goes back to 1 under this function. So indeed, 2 goes back to 1, because this function takes 2 to 5, this function takes 5 to 1. So overall 2 goes to 1. So that's alpha times beta. What is beta times alpha? Again, I'm going to start the same way. I'm going to try and figure out what 1 does. So this function takes 1 to 2, and then this function takes 2 to 5. So 1 goes to 5 under the composition. Okay, what does 5 do? Well, this function takes 5 to 1. This function takes 1 to 4. So I think 5 goes to 4. Okay, this function does nothing to 4. 4 just goes to itself. So 4 gets passed over to this function, which takes that 4 to a 2. And then finally, 2 goes to 5, and then 5 gets passed over here, and 5 goes to 3. So 2 gets sent to 3. And then I think 3 is probably going to have to go back to 1, but let's check. 3 does nothing over here. 3 gets sent to itself, which means 3 gets passed over this function, which takes 3 to 1. And there we go. Again, we have an alpha and a beta, which do not commute. Alpha beta and beta alpha are two totally different permutations. So anyway, that was an example of how to do composition in cycle notation. And this is what I want everybody to try and get good at by doing some practice later on.